Good morning, all. I apologize for missing today's lecture. I'm going to go through a review. I'm going to start off with one concept that we didn't really talk too much about, but it's pretty straightforward. So we're dealing with solvent effects or solvents for SN1 versus SN2. The concept is if I'm doing a reaction I add in NaCl. So the Na makes this aprotic. We want to make sure we don't add in a solvent that is protic. So for this here, in order to do an SN2, if I was to add something in like DMSO as a solvent, this is aprotic. Doesn't have a proton donor anywhere. So this would work well versus if I was to add in something that is protic, like let's say I added in ethanol here, ethanol is going to mix with NaCl and give me some combination of HCl plus O and A here. So it's really not going to give me an SN2 reaction in this case. It's going to force it to SN1 because I'm making HCl when I add in a protic solvent. This one's protic. So this would end up giving me my SN1 reaction. Just because I didn't use the right solvent, it's going to force it towards the wrong reaction here. So when we're doing these SN2s, we need to use aprotic solvents, and then for SN1, you could use an aprotic solvent. Alright, so I'm going to talk through, it's kind of starting at the beginning of things we haven't talked about in a while. So talking about some radical reactions. We've got 3 different radical reactions we've covered. Br2 in light, I guess 4 if you include Cl2 in light. So Br2 in light is going to brominate at our more substituted position here. We've got Cl2 in light, which you can do some math to figure out where it goes, but I'm going to skip that one for the moment. We've got Br2, let's put a double bond on here, and peroxide, or sorry, HBr and peroxide. This is going to give us our anti-Markovnikov product. And then lastly, the one that we talked about at the very beginning of this unit, oof, a little rough, was NBS and light. So NBS gives us a vinylic radical. So we're not going to go through the whole mechanism. We're just going to kind of cut to the point where it's going to pull off, in this case, this vinylic proton here, giving us a vinylic radical. The vinylic radical is going to have 2 different possible resonance structures. And we're going to see which one has the more stable double bond of them. So there's this resonance structure as well as this one here. This double bond is only got 1 group coming off of it. This one has 3 different groups coming off it, so this one will be more stable. Our bromine's going to end up where that radical was. and we're going to get this bromination product. So MBS is going to give us our vinylic bromination. Let me do one more if we have something that is like this here. Now we've got two different vinyl positions. So our double bond is here, one position away. We've got a tertiary and a primary. We're more likely to pull off that tertiary position in order to make our radical. From this point, looking at our two resonance structures, we're using half arrows for these because we're moving around a radical. Di-substituted versus tri-substituted. Tri-substituted is more likely to go to our product. Should end up with this bromination product here. Alright, let's talk a little bit about alkenes and alkynes. So making an alkyne, we're going to do eliminations to make these. We can either do eliminations where both of the leaving groups are coming off at the same position. So if I added a large base here, or a small base realistically, this is going to generate initially we'd pull off a proton, make our double bond, kick out one of these two BRs, and then with a second equivalent, oops, it needs to be linear, lose that other BR and generate our alkyne here. Similarly, if they are staggered or one carbon away from each other, we're going to form the double bond in between the two of them. Let's see. You would initially make more likely to pull off this one first. But then it's just going to do a second elimination immediately, so you're going to get your alkyne here. We can use double bonds in order to form these. So starting from a double bond here, if we throw in Br2, we can dibrominate. And then from this point, adding in terbutoxide would let us generate our alkyne. As a quick review, a whole bunch of reactions you can do with an alkyne. If we had an HBr, can brominate, HBr2 equivalents. Br2, two equivalents. Similarly, let's see. So H2SO4, H2O, HgSO4. It's going to get us into our ketones. BH3THF. NaOH peroxide. Can also do alkylations. NaNH2. Some sort of alkyl halide. I would add the 2 carbons here. Reductions. We had an H2, we can completely reduce it. Well, let's take this one. So H2 for this one. Platinum. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. H2 and Linlars. It's going to give us our cis double bond. And then Na and ammonia will give us our trans double bond here. All right, let's talk through our 4 different types of reactions. In this main portion of it. So our 4 different types are SN2, SN1, E2, and E1. Okay, so SN2, this is our binucleophilic substitution here. Going to add an aprotic nucleophile, NaCl. We're going to end up inverting our stereochemistry, like so. It's going to happen through a one-step mechanism. Because it's happening through a one-step mechanism, our rate law is going to correspond to both our alkyl halide as well as our nucleophile here. So in this case, our rate would be this alkyl halide times the concentration of NaCl. If we want to think of this as an energy diagram, it's all happening in one step. So as the reactants, products, no intermediates forming here, it's just all going to go immediately to our product. Okay. SN1 is our 2-step addition or substitution reaction. We're going to add in a protic nucleophile, something like HCl. Br is going to leave, make a positive charge. At this point, there is no stereochemistry. There's no large Br blocking one direction. So our Cl minus can come in from either direction. It doesn't care. It just sees a negative spot or a positive length spot. It's going to give us this product here. Our rate limiting step is going to be this first one. So because of that, our rate is equal to, in this case, just the concentration of our alkyl halide. From this point, because we're doing 2 steps here, our energy diagram products, reactants, we are going to see that second step here. So this would be our intermediate. from our reaction. Largest energy barrier is going to be rate limiting, so this is our EA. This is our rate limiting step here. Using red. Okay. Our next one is going to be our elimination. Technically, there's two different types. I'll do E1 on another page. I think I'm going to run out of space. So, if we add in, let's start with large bases. A large base like so. This is going to be selective for our less substituted position. In general, here we can throw another group on here. The more substituted position is the better position to pull off of. If I look at this, our alpha position is where the bromine is attached. To have beta and beta here. Technically speaking, this H should be the best one to pull off in terms of stability. The problem is I have all these electron clouds surrounding it, which makes this really hard to get to. So if something large like this large base here, it's going to have a really hard time to getting to this. It's going to have a much easier time getting over here. So it's going to be selective for this less substituted position, kicking out our bromine to get to our product here. It is all happening in one step, so our rate would be K times concentration of alkyl halide, and then times the concentration of our base here. It's happening in one step. So no intermediates forming. Just to kind of review our small base, very similar. It's just going to have an easier time getting into that hard to reach area. So NaH should be considered a small base. It's going to be able to get into this tinier area. Forming this other double bond product here. All right, E1. This is our two-step process. I'm going to draw for an alcohol. And use H2SO4. So we're going to pick up an H plus. And we're going to lose the water. So we'll make water here. It'll move out. I'm just going to draw the water leaving. It's going to give us a positive charge. In this case, this one can rearrange. Can do a hydride shift. It's not going to overall affect your answer, but it is possible here. From this point, we made HSO4 minus, which is a small base. It's going to pull off this more substituted position to give us our other elimination product. Okay, so rate law for this one. Loss of this leaving group is going to be our rate limiting step. So it's going to be based on the concentration of our alcohol individually. In this case, we had 3 steps, so our energy diagram would look something like 1, 2, 3 to get to our products. Oops, P, not R. Okay, we have a large table that kind of tells us which one to use when. I'm going to draw that in landscape, I think. So, on the column side, we're going to have primary, secondary, tertiary. On our first column is going to be strong nucleophiles. These are things like NaCl or KCl. The counter ion here isn't that important. NABR, NaI. These are, on a primary center, we're going to do SN2. On a secondary center, also SN2. On a tertiary center, it's just 200. It's going to do SN1. That leaving group has to leave first. The only way it's going to happen. We have our non-nucleophilic strong bases. Things like NaH, our large base, so T-butoxide, LDA. These are things that are going to do eliminations. They're probably going to do some combination of E1 and E2. Here, generally speaking, they won't do any sort of rearrangements because they're already on a tertiary center. So they're going to give you the same product either way. Okay, and then our combination one, so strong nucleophile, strong base. And we're just going to say E2 for this one. So NaOH, methanol, or Na methoxide, sodium methoxide, sodium methoxide, ammonia, put a methyl group on the nitrogen, etc., something like that. These are going to do SN2. When we get to the secondary, it's going to end up doing both. Slash E2. And then our tertiary ones is just going to do E2. We can have our weak nucleophilic. This could be things like HCl, HBr, HI. These are still going to do SN2 in a primary center. you're not going to make a primary carbocation. It's just way too unstable, but you'll get SN1 here, as well as SN1 here. So kind of looking at some trends, these two kind of group together. They're mostly SN2 for primary, SN1 for tertiary, and then you get the flip of SN2 versus SN1 here. Our bases are mostly just going to do eliminations. If it's both a strong base and a strong nucleophile, for primary it's going to do SN2, tertiary it's going to do E2, and then for secondary it's going to do both here. All right, let's talk through some and there's one more category, which is weak nucleophile, weak bases. These tend to be a little messy. They're things like methanol, water, ethanol. They're protonated here. They tend to do pretty much nothing in primary centers. And you end up with usually some sort of mix of SN1, E1. Same thing here, SN1, E1. Let's talk about some alcohol groups, and then I'll get this video sent out to you guys. Okay, so we've got alcohols are notoriously bad leaving groups. We can make these better by protonating them, so adding in something like HCl. If we make water here, this is actually a pretty good leaving group. So this could leave, giving us a plus here, Cl minus can come in. And give us our product. Tend to get a little messy, they tend to rearrange, things like that. So the way to get around to this is we use Tosyl groups. So if I add in TS chloride and pyridine, it's essentially going to do an SN2 and kick out the chloride here. And generate this good leaving group. OTS, we can kind of treat it just like it's a halogen. It'll do pretty much anything a halogen will do. So if I add in NABR, I'm just going to do a regular SN2 here. Adding a small base. Should give us a double bond at our more substituted position. Large base. It's going to give us that double bond at our less substituted position here. I'm going to walk through a couple mechanisms and then probably call it for this. So let's do a E1 using an alcohol. Let's do a complicated one. do this one here. So if we add an H2SO4, first step is we're going to pick up a proton. Make a water here, we can have that leave. We're going to do a rearrangement in this case. We have a secondary carbocation that's next to a tertiary center. So we can do a hydride shift. At this point we're doing an elimination. So we've got our alpha position is going to be where our positive is. We've got 3 different betas here. We've got a beta here, beta here, beta here. This one is primary, secondary, tertiary. HSO4 minus is considered a small base. So we would pull off this tertiary proton in order to get our product. Which would be this here. I'm going to talk through one more mechanism just to do it, which is going to be let's do our tolusyl chloride mechanism. It's a good example of SN2. So, taking an alcohol, I'm going to make it a little simpler just to write a little bit less. So our tolusyl chloride looks something like this here. Let's do one tolusyl chloride pyridine, and then I'll do a SN2 on top of it. So let's add an NaCl. We are going to have a nucleophilic attack on the sulfur. It would kick the electrons up to our oxygen, back down, and then kick out our chloride. From here, our pyridine, 6-member ring with a nitrogen on it, can pick off this hydrogen, giving us a neutral compound. Our OTS group now if we add an NaCl, we can build up a higher amount of Cl than just would be released by the tolusyl. Do a nucleophilic attack here. And get our chlorinated product. So this allows us to do SN2 with an OH. Alright, thank you guys for listening. I hope you guys have a good day.